Hello. There is some interruption in the university network also. So, are you with me now?
Yes, sir.
Okay. Sorry. So we will continue from there onwards. Sorry for the interruption. It seems the network is not stable even in the university. I don't know why. Just a minute. In the meantime, please put your name and number in the chat box. Okay. So there are some low velocity zones because of this P and S wave transmission. So we were talking about the within the mantle, there are some low velocity zones. Actually, the asthenosphere. Can you remember we did some aspects of the asthenosphere last time? So there, uh, both S and P waves are transmitting without the trouble, right? I think last time I mentioned that P waves are traveling through solids as well as in liquids, but S waves can travel only through solids. That is you have to understand because do you remember the animation which I showed you about the P and S waves, their properties? Animation showed you that S waves are sort of shearing type of motion, right? So this shearing type of motion is not facilitated by fluids or liquids. Okay, so for that you need to have a robust medium. That's why S waves are not transmitting through liquids, but P waves are compressional, so you can compress liquid without any problem, right? Like you apply brake in your vehicle, it's fluid, right? Fluid is there which is compressing, right? So like that, P waves can be transmitted through both solid and liquids. So in the asthenosphere, both S and P waves are transmitting. So what is the meaning of that? Asthenosphere should be a solid material, right? It should be a solid material, but there are some instances where S waves are interrupted there. S waves are interrupted, right? So that means uh, it shouldn't be all solid in that case, because S waves are not transmitted through through liquids. Interruption means the medium is not entirely solid. So that's why we call the asthenosphere is semi-solid. Okay, it's like a gel-like behavior. Some places it behaves like a fluid, right? Therefore, there are some interruptions. So that is what you call some drops. So these S waves are discontinued there, right? Continuously you can see their transmission because of this particular behavior of the asthenosphere. So therefore, the scientists have understood that asthenosphere should not be a complete solid, but also not a complete liquid. So that's why it's called a semi-solid. So this is how their properties were determined. And uh, then there is another discontinuity recognized by this P wave changes uh, at about 400 and 670 kilometers. So there are two discontinuities. One is at 400 kilometer and 670 kilometer the next one, right? So this is the depth from the surface. Okay, So sharp P wave velocity changes are there. Actually, this is attributed, even experimentally it has been proved that this is not because of a change in a layer, right? It's the previous discontinuities were entirely because of a layer change, that means crust and mantle. But here still we are within the mantle, right? The lower part of the mantle now. It's 400 kilometer means still within the mantle, right? You can remember the cross section of the earth and just check the depth of 400 to 600 or 700 kilometers. Still we are in the mantle, but not the uppermost part of the mantle, uh, the lower part of the mantle, right? So uppermost part of the mantle is the asthenosphere, right? Which is we just mentioned that it's a semi-solid type, right? So the next type uh, is the lower part of the mantle. Within the lower part of the mantle, still there are some discontinuities. So these discontinuities are actually not because of a physical layer change, right? Still the same layer, mantle, is continuing. This change is because of some phase change. Scientists have attributed that to phase change. So what is phase change? So here you can see the phase change. Phase change means mineralogical change. Okay, phase change means a mineralogical change. So mineralogical change means the layer beneath. I mean the layers. There are some heterogeneous layers within a single layer. That means within the mantle, uh, you have uh, you have a separate phase. Separate phase mean there is a uh, mineralogical change. Okay, so mineralogical change means some kind of a for example, olivine you have in the mantle. Remember peridotite, right? The mineral. So that can change into some other form. That means some high pressure variety of olivine. Chemistry does not change. That is the most important thing. Chemistry does not necessarily change, but the crystal structure changes. Okay, so it is more the atoms are arranging into a more consistent with more compressed form. That means that is related with the pressure. When you go deeper and deeper, for example at 400 kilometer means it's very deep in the mantle, so the pressure gets increased drastically. So there, under high pressure conditions, atoms can rearrange into more denser configuration. Okay, so for that, to enable that, some phases, some minerals which are used to be in relaxed form at shallow levels can be changed. The structure can be changed, but not chemical change. Okay, so actually these type of minerals change. For example, olivine, garnet, pyroxene, and quartz. These type of minerals can change into more high pressure type of varieties. We call peroxide. Uh, Peroxide. It does not mean hydrogen peroxide like peroxide, right? Okay, it's a perovskite, right? And more high pressure garnet, right? Wadzlite. There are several types of minerals, high pressure varieties. You can search them in the internet even. The high pressure mineral forms you can find. But it is not very, you don't need to go into much details, but just keep in mind that at deeper levels, these minerals are formed. Actually, these type of samples are not available for us. I mean, 400-kilometer depth, there is no way for us to access this depth. Even drill, you can't drill that much, right? Even we know about some tens of kilometers only. I mean 20 a few 12 kilometers depth, the most detailed borehole, the deepest one, right? So only thing is when we get some samples from magmas like mantle plumes, right? Even normal magmas are coming from the asthenosphere, right? They are not that deep. But the magma that I mentioned about uh, the heating of the supercontinents, plumes, mantle plumes, remember? They are coming from the core mantle boundary, even deeper. It's some thousands of kilometers deep. So these magma can bring some rare samples of these very deep materials. So there you have the natural examples of such high pressure varieties. But now the high pressure laboratories, we call them experimental petrology laboratories, have been able to produce this type of high pressure varieties in their labs, right? So there for that purpose there are different piston cylinder apparatus, we call piston cylinder apparatus, because you have to increase the pressure in in a given vessel, right? So into this vessel very high pressure is applied, right? Some materials are put there, for example some peridotite materials or some basalt materials are put there, and people observe increasing pressure, right? Increasing pressure and also temperature, because it should be equivalent with the conditions available in the Earth's interior. So people have gone through such experiments, and they have been successful in generating this material in the lab, right? So high pressure varieties they could generate. So by that they have understood that the Earth's interior has these high pressure varieties, and this has been reflected by sharp p wave velocity changes, okay? Because the material change matters for this wave increase, right? Density also increases, so therefore p wave velocity increases. So these have helped us to figure out the Earth's beneath or the interior. So that is very important. And also another factor supports this seismic wave propagation and their behavior, which we call the seismic refraction and seismic reflection. Seismic refraction means the bending of seismic waves. That means bending of P and S waves when when it is penetrated down in an earth. Uh, it's like it's changing their direction, right? If you penetrate a wave, for example, the easiest example is the light wave, right? You just take a torch and aim it at a well or a water body, right? So you if you can find its propagation direction, you will definitely see the angle at which you shooted your light wave will be changing when it just meets the water surface. So that means it bends, right? The direction changes. So such kind of change happens even for P waves and S waves when they hit rock layers, different rock layers. When they hit, if the composition is contrastingly different, then this wave can considerably change their direction. So that is what you call the seismic refraction. And some seismic waves come back. That means bounce back. That is what you call the reflection. It is something like you aim a torch towards a mirror, right? So you can see some reflection, right? It is coming back. So similar thing happens for the seismic waves as well. That is what you call the reflection. So by these properties as well, people have tried to figure out the Earth's interior compositions. That means more denser the material, the faster the velocity, right? So that is happening, and this feature has, I mean, this seismic reflection and refraction aided the scientists to find another boundary. That is another, I mean, very important boundary, the second major boundary, that is the core-mantle boundary. So previously Moho was there, that was the crust and mantle boundary, right? Now what we have is core-mantle boundary. So this was discovered by Gutenberg, right? German scientist. Uh, so therefore this is named as Gutenberg discontinuity as well. Discontinuity means some kind of physical change, okay? So you know outer core. First to meet is after mantle is outer core, right? So that is the starting point of the core. So that's why it is called the core mantle boundary. But first to discover, first to recognize, or the first to find is outer core, which you know is a liquid. So that means P waves can travel through the outer core, but not S waves, right? So that is important. So sudden disappearance of S waves have been recognized by these experimental people, the scientists, so they understood that okay, there is a liquid layer inside the earth as well, right, at this depth. So later on, this was found that the combustion was iron and nickel. And anyway, this discontinuity was called Gutenberg discontinuity because he is the one who led these experiments to find this core mantle boundary. Actually, this is the place where these other type of plume magmas are generated. Very rarely, once in once in 300 or 400 million years time, uh, this type of magma eruption is taking place. Actually, it takes time to come up to the surface as well. That is the reason for it to take that long, right? Because you have to reach some thousands of kilometers from the core mantle boundary to the top of the earth. That is also one reason not to have it frequently on the surface. Okay, and phi waves are refracted. P waves are refracted. That means they are bended, right? So they change the velocities as well. Uh, because of refraction, the change happens. The velocity change happens. Because of this bending, what happens? The wave bends and therefore it enters the core very steeply, right? Because of this bending, right? Because the core is more denser than the mantle, because core is composed of iron and nickel, so it is more dense than the silicate materials in the mantle. So therefore, P waves get bended very much. And this bending is also some systematic observation is there. That means phi waves die out at 105 degrees from the place where it was started, and reappear at about 140 degrees. So what does it mean? It means about 35 degree. That means 105 to 140. That means 35-degree difference. The angular difference is there where you can't see these P waves. So this white region is called the P wave shadow zone. So I just uh, I will show you some example for that. It's a kind of disappearance of a shadow zone, P wave. Okay, disappearance of P wave in that region. So I will show you some example. So let's see whether you can find this. Okay, can you see this figure? Yeah, is it visible clearly?
Yes, sir.
Shadow zones. We call them seismic shadow zones, where at I said 105 to 140, right? So this is the place where the wave started. So it goes directly to the uh, interior because it can travel through both liquid and solid. So outer core is also liquid, therefore, but still it can travel, and you can see this bending. You can see this bending. That is what you call the refraction, seismic refraction. Okay, but there are some region here. For example, this red or orange region here. There are no wave, right? So from here to here, there are no wave. So this angular difference is like about 35 degrees, right? So this 35-degree region, you can't see any seismic wave. So actually the seismic stations to detect these waves are located all over the crust. That means you start explosion here, and the detectors are installed here, and everywhere around the circle, right? Then the detectors which are available in this region says that they did not recognize anything, any seismic wave. So that is because of some seismic shadow zone. Actually, it's not very clear as to why this shadow zone is appeared there for P waves, probably because of they are reflected, right? The belief of the scientist is that they are, without refracting, they are reflected, right? Reflecting means they are bouncing back to the surface, right? So for the light wave also there is a critical angle. We call it refraction. Okay, so this is what you call reflection, right? So in that zone you don't see any seismic wave. Okay, that region you don't see any seismic wave. So this type of shadow zones are there. For S waves are also some shadow zones are there, but you know, the S waves cannot travel through this liquid region. Okay, yeah, because outer core is liquid, so it is not possible. So this type of changes, or this type of variations are recognized through this seismic wave behaviors. Okay, so this is how people have come into some conclusions that this seismic refraction and reflection has happened within the Earth's interior. Okay, so so these actually these things have been confirmed with the experimental things as well. So therefore, there is no doubts about these things. So people have now well established structure using these type of these type of experiments. So mainly this outer and inner, the next boundary is the outer core and inner core boundary, right? So it's called the Leeman discontinuity. So it's, you can see here, it's called the Leeman discontinuity. Leeman discontinuity means the boundary between the inner and outer core. So now you can, I think, recall the boundaries. First we had the Moho. Okay, after Moho, there were only some phase changes at 440 and 670 kilometers, but not a physical layer difference. It is still within the mantle after the Moho. Then what you got was Gutenberg discontinuity, which is the core mantle boundary. Okay, core mantle boundary. And after that, what you have is outer core and inner core boundary, right? Outer core and inner core boundary. That means when you enter the outer core, you proceed downwards and then you will meet the inner core boundary. That is it, right? That is Leeman discontinuity. So this Leeman discontinuity is understood by a sudden increase of seismic velocities, as I mentioned before, because that is solid, right? It's solid. That means the density is more greater than even the outer core, because even outer core is still the same material, iron and nickel, but it is liquid, right? But when you come to the more interior, it's very, very high pressure conditions, more than the outer core. So therefore, these materials are again get solidified. So you have change in seismic waves there as well. And this discontinuity is mainly because of the presence of solid iron as solid inner core inside, right? So this is how the scientists understood about that core structure in there, right? So P and S waves are very useful in identifying this type of features. Actually, it is not only understanding the Earth's structure, but also to understand some other solid space materials. People have uh, used seismic waves, and this has helped immensely to understand the physical properties of materials, right? Physical properties of matter, actually. So this is very important. Do you have any questions until that section? If no questions, so we will continue then. So in addition to the seismic evidence, right? So these are seismic evidence. So in addition to this seismic evidence, what we have is the gravity anomalies also, right? People have considered gravity anomalies as well to understand the structure of the Earth, right? So more details or some other extra aspects, people have used gravity. So what is gravity? Gravity, it's because of the attraction of masses. So once you have a mass for a material, definitely there will be a gravitational field, right? So Earth's gravity means uh, we are having the Earth's gravity because the Earth has a mass, right? Earth is a huge mass, so it can attract any material downwards to it, right? So that's why, unlike the space we have, or unlike the moon even, we have a higher gravity than the moon or the space. So because of the huge mass we have, right? So the anomalies of this available gravity, or the gravitational field, we call gravitational field, it's like a magnetic field, right? Around a magnet you have a magnetic field, right? So that's why when you make closer the iron dust, the magnet can attract them because of magnetic field. So likewise, gravitational field is also there. So this gravitational attraction also changes in some place to place in the Earth. So that indicates some physical changes are there even in the Earth's crust, right? So crustal homogeneities or heterogeneities can be recognized with the help of gravity. For example, if there is a place where you have uh, iron deposit, right? You understand iron deposit. For example, what is the mineral which is abundant in iron deposits? Can anybody tell me a name of a mineral which is available in iron deposits? Any guess? Some people get misled as to this may be a meteorite or something. It's magnetite, right? You know magnetite. Magnetite is a mineral which is available in iron deposits. Iron deposits means sometimes you can see these iron deposits like hillocks or hills, right? Some small hills. If you go to Buttala, Vellavai region, there are such iron mountains, right? So these are magnetite, full of magnetite. These are mountains which are full of magnetites. So huge magnetite deposits are there. So the around these regions, gravity anomalies are also there. In addition to, they have magnetic properties as well. So magnetic anomalies are also there. The gravity anomalies are also there because they have the sudden changes of densities there, and therefore they attract materials great in a more intense manner than the other materials, right? For example, if you have a hill or hillock made of quartz, that means Sirwana, right? It will not attract much, right? Because its properties are different. But if you have a magnetite deposit, it can attract or it can change the gravitational field into a great detail, right? So this gravitational attraction can also indicate some inferences on the density of the material which are available as rock layers. So normally the Earth's average density is about uh, 5.5 grams per cubic centimeter. 5.5 grams per cubic centimeter. So therefore, some density changes are there. You can, I mean, you can detect some density changes when it deviates from this number. Right? This is the average density. This is the average density. If you measure some density in a region, average density in a region, that means if you measure the densities of some rock layers available in some area, if you get some different figure, if you get some different value, that you call a gravity uh, difference. The density difference reflects gravity anomaly. So we call it anomaly because it's different from the normal average value. So average crust and upper mantle densities are normally around 2.7 to 3.5. The mantle is more denser than the crust, as you know already. So which is about 3.5. So the crust, maybe the normal crust, it's about 2.7. But you know, the average Earth's density is 5.5, just we mentioned above. But the crust and mantle, which is composing the most or the dominant part of the Earth, is only about 2.7 to 3.5. So balance. So how come this 5.5 comes as average? This is this much, right? So that means there should be something else of, I mean, some other layer which is must be of great density than 3.5, even than 5.5, because the average is 5.5. So you must have higher values to get this average. So what is that then? The core actually, you know, it's made of iron and nickel, so it should be much more denser than the mantle and core. So actually the core density is like 10 grams per cubic centimeter, right? So which is consistent with the densities of iron and nickel, the metal densities. So that comes as once you take everything into average, it will figure out up to like 5.5, right? So that's how these densities are variable within the Earth's interior. And when this average density changes, means around those regions there should be some changes in gravitational field, because gravity is always related with mass. Density is also related with mass. Okay, so density changes means mass changes. Again, that causes gravity changes. Okay, so that's why gravity anomalies are found in the Earth depending on these materials. Right? If you have a iron deposit, right? If you have an iron deposit on the crust, on the surface, right? In some countries you have iron deposits, right? We also have some iron deposit, copper iron deposit in Seruvilla. If you measure the gravity field or the gravitational field as a cross section from one side to another, you will see clearly difference in gravitational field, because you know at that particular deposit area, uh, density difference is there, local density difference is there, so that causes gravitational change, right? So that's why people use these gravity anomalies to recognize, to explore mineral deposits on the top of the Earth's surface, everywhere you see some soil plus some rock layers, but you can't see iron deposits or any other special type of deposits very easily. But when you do some exploration, that's why we do some geophysical explorations to understand the gravity anomalies and all. When you explore or when you hunt for mineral deposits, right? So once you recognize some sudden change in the gravitation field, then you explore, you detect that region and do some detailed explorations. For example, these gravity surveys can be done uh, using aircrafts even, right? So they can detect, the aircrafts can detect, or aircrafts or the surface driven instruments. We have instruments to detect the gravitational fields or magnetic fields, magnetometers, gravitymeters we have. So using those, you can detect some gravity anomalies, right? Anomalies means field differences. So once you detect this type of anomalies in that particular region, you can select and do some detailed investigation, and you can find some mineral deposits, right? So if you have some metal deposits, then definitely there will be some gravitational difference. So this is how the geophysical investigations are taken to recognize the mineral deposits. But this technique cannot be directly applied to gemology. The reason is the gem minerals are mainly oxides or silicates, right? So oxides or silicates, so they don't have very contrasting differences in densities. Of course, density is higher. That's why you can feel some heaviness when you take a gemstone onto your palm, onto your hand, but it is that density is not contrasting enough to detect in that sort of a gravitymeter or such instrument to recognize an anomaly. Actually, the gem beds are distributed, but everywhere you don't see the gemstones, although the bed is there. You have pebbles, rounded type of stones, mostly quartzite, right? Mostly quartz. It's normal crustal composition, so you don't see much difference in densities, although you have some rubies, sapphires hidden inside. But everywhere you don't see these ones, right? But in an iron deposit or some metal deposit, it's a superficial, or it's a changing. I mean, it's a distributed over a huge region. The quantity is very large, but the gem varieties cannot make that sort of a contrasting anomaly to to be detected by such a machine, such an instrument. Okay, therefore it's difficult to apply these geophysical exploration techniques for gemology. Otherwise, people have explored much more areas for gemstones, gem varieties. Okay, right. Anyway, so these are very useful. These anomalies can be positive or negative. Positive means it's giving a higher density contrast. That is happening because of heavier rock. Heavier rock means this rock contains a lot of dense materials, like for example magnetite or zinc sulfide we call sphalerite, or even gold, right? Those are heavy. And also if they are distributed uh, intensively in an area, so they can give a contrasting field anomaly, right? So negative anomalies are produced by lighter rock. So what are the lighter rock? For example, there are some low gravity uh, fields generated by some lighter rocks. For example, there are in some countries we have something called salt domes, right? Salt domes. That means sodium chloride. Actually, they are salt, natural salt. It's not. It's not because of somebody who concentrated seawater and produced salt, right? It's natural salt. Salt is also a mineral. Sodium chloride is a natural mineral, right? It makes some domes like features in some regions because of precipitation. Some time ago, if land was submerged by oceans, right? Such areas are there. Some seawater precipitations are there. right? So they are natural salt domes, dome-like. Dome is like a cave-like thing, right? Uh, Such deposits are there. So if you have a regional scale that salt domes, then the gravity will be low. There will be some low gravity zone shown, and also some sedimentary basins. Sedimentary basins means not hard rocks like sandstone, limestone, or siltstone. There are several sedimentary type of rocks, or even low density varieties of like coal or something like that, right? Such areas also show some gravity anomalies, low gravity anomalies. So we call them negative gravity anomalies. So such anomalies are also helpful to understand the heterogeneity of the earth, right? For example, in this case, mainly we understand the heterogeneity of the crust, right? Not the very deep interior. That's why we have to penetrate some P and S waves to understand the interior, right? Interior you can't detect by the normal anomalies, I mean normal gravity anomalies. Superficial things, I mean around the crust you can understand these gravity type of anomalies. So another feature of these gravity anomalies is it is controlled by isostasy as well. What is isostasy? Isostasy means the balance between the overlying rocks and the balance of these rocks on top of the mantle. Crust is on top of the mantle. It's like you when you press a cube of ice on water, right? What happens? It always tries to come up, right? It always tries to float or come up, right? Even it tries to float, you can press it with your finger downward so that it goes inside the liquid or the water immersed. But as soon as you remove your finger, what happens? It comes up. So that is isostasy, right? There should be some balance because it can't bear that pressure, and density is different. It's light, so it floats up. So likewise, we have some rock layers. The mantle is more denser than the crust, so therefore it's like floating ice cube, like, right? The crust, you can compare it with, like, right? So once you remove the mass of this crust, what happens? It becomes more and more lighter. The mass reduces. So the removing mass means you are removing the gravity, right, of that particular region. So then not only it creates a negative gravity anomaly, but also it creates imbalance in the isostasy. So that means from the interior, the below line rocks beneath that region tries to come up. That is what you call the upliftment. That's how the deep interior rocks are exposed on the surface now, right? They were lying in at the interior some time ago, but once this weathering takes place, erosion takes place, materials are removed from the top. So then gradually these interior rocks are coming to shallow levels. That is how this happens. So there you have a negative anomaly. And also at places where you have the mountains, the mountain building regions, so you remember the continental collision. Continental collision creates some belts of mountains, right? Remember the mountain belts? So there what is happening? You are accumulating some mass on uh, towards a region, localized region, where you create some mountains, like, right? So generate mountains. So there what is happening? There should be uh, there should be some positive gravity anomaly, if because you are accumulating materials into one region. So there should be some gravity anomaly, but actually uh, it is not expected. I mean, it is not seen very clearly, this anomaly. That means if you have a mountain, wherever you have a mountain, there should be some gravity anomaly, but it is not the case, right? Unless you have some specific materials like the Buttala case, right? The magnetite case. So if you have a lot of iron-rich materials in that mountain, then definitely you will see a positive gravity anomaly. But if you have the normal rocks there, you will not see this gravity anomaly, because there is some there is some balance coming as a result of this isostasy, right? So once you have this the mountain regions built up if it is not consists of these heavier materials like iron or something, this contrasting gravity anomaly will be not seen, because uh, based on the isostasy principles, once you have a mountain, no sooner it starts erosion as well, right? Erosion and weathering and everything is happening. To compensate that, the mantle also brings up some materials towards that means the upliftment also starts at the same time where the erosion starts. So therefore some balance is there. So therefore this extra mass will not create much gravity anomalies due to that isostasy case, as well as some of these heavy masses. For example, once you create a mountain, you are generating a huge mass, or you are concentrating a huge mass into a localized region. But uh, as a result of uh, as a result of this isostasy, not only the materials coming from or the upliftment, the block of this huge mass tries to sink downwards as well, right? Both things are happening, sinking downwards because of the heavy mass. For example, if you have an iceberg on the ocean, it sinks first, right? It sinks downwards to some extent, right? Because of its mass. But still it tries to float on the water because of density difference, right? But it sinks down as well as it tries to float. So both things are happening. That is what you call the isostatic balance. So this happens on the Earth's crust as well. Here, the mantle behaves like an ocean, the crust behaves like an iceberg, right? So both things are happening. Therefore, there will be no much contrasting gravity anomalies seen around the mountain belts, unless these mountains are composed of high dense material like iron or some other zinc or some other heavy metal, right? The natural metals are there in the forms of minerals. For example, iron is composed in magnetite, pyrite, right? Like there are different minerals. And also this zinc is composed in sphalerite, zinc sulfide, those are sulfides, right? Sphalerite and lead, for example, they are in galena, a mineral called galena, right? So these are the natural materials you can take these metals out of, right? To extract these metals, these natural minerals are used. So unless these type of metallic minerals are available in mountains, you will not see a contrasting gravity anomaly considerably. Okay, so that is normally happening with regard to the isostasy, and this causes some imbalance in between, right? So anyway, to understand the structures of the earth, this gravity is also important, right? So this is very important. And also you can consider the Himalayan mountains. Himalayan mountains, as you know, it's like kind of stacking of Indian and Asian plates. Like you are compressing two plates together, and makes more uh, heavier mountain belt. And because of increase of mass, it can even sink down to the lithosphere, the mantle as well, as I mentioned, like an iceberg. So that balance also maintained there as well. Okay. And as I mentioned before, the erosion also plays an important role to make this balance, isostatic adjustments. So those balances are there. So therefore, you can't see clearly some gravity anomaly, right? So normal gravity is there, existing, but unless you have a specific material like magnetite or sphalerite or galena or something like that, or gold even, you will not see a contrasting gravity anomaly, right? Because of this isostatic adjustment. We call them isostatic adjustments. Okay. Okay, so some ice or some glacial ice can also cause this type of rebound, isostatic rebound, because in polar region now we have ice caps. Once the temperature, global temperature increases, these ice caps get melted, and what happens? Their weight on top of the lithosphere is releasing. So then these the pressed lithosphere can be released by melting of these icebergs. So that can also cause some rebound, and some sudden gravity changes can happen because of such reasons as well, right? Because at once, if you have some contrasting mass differences, then for a certain period of time there can be some gravity anomaly, but later on it is adjusted by the isostasy. So that is we call instantaneous changes in gravity. Instantaneous changes means for a very short period of time, these gravity anomalies are happening, right? It can be, this short period means it's not like 1 second or 1 minute or something like that. It's a geological sense, right? Short period means maybe some hundreds of years. Okay. So the magnetic field, the other thing is the magnetic field. So people have studied about the magnetic fields as well, like the gravity field. So Earth's magnetism is also has some characteristic features. As the Earth's magnetism has been caused by the Earth's core. Okay, why is that? Earth's core is composed of iron and nickel actually, but iron is also there predominantly. So it behaves like you are hanging a bar magnet uh, on the surface of the Earth. So if you have a bar magnet there, there is a magnetic field from from their polar sides. I mean, the magnets poles are there, right? Magnets, remember, north and south is there in the magnet also. So from north to south there is magnetic field. So similarly, uh, it's like at the interior you have a big magnet, huge magnet, right? So this magnetic property is there, which has been generated by the Earth's core. Actually, the interior of the Earth is too hot, right? So actually, there is no magnet existing at all, but it can behave like uh, a magnet is there, right? So the reason is the magnetic field is generated. As you know, the outer core is liquid, inner core is solid. So once the Earth is rotating, there is possibility for this core also to rotate, right? But the important thing is the rotation of the Earth's core is more rapid than the Earth's normal rotation, right? And also it's kind of a little bit oblique than the normal axis of the Earth. So therefore, it's like a dynamo. It behaves like a dynamo, right? You know the dynamo. Dynamo is moving electric current, and then it causes it's moving magnetic property that creates electricity uh, for us to use, right? So likewise, this moving magnet, moving iron inside the Earth's core can generate electromagnetic features. So it is more like electromagnetic material existing inside the Earth, right? So the Earth's core must be an electrically conducting fluid. The fluid is there, right? Outer core is the fluid. So this iron, nickel, both would work together to make this magnetic field to produce. So Earth's magnetic field is produced by this one. So, so the core produces this Earth's magnetic field, and it's very important because that is very strong. That is very strong, and we feel it on the surface as well, right? Earth's surface, we feel the magnetic property, which is generated at the extreme deep of the Earth, some 6,000 kilometers below. So this inner core rotates faster than the Earth's surface. That means there are two rotations in the Earth. The normal outer region rotates at a slower velocity than the Earth's core, right? So it's very rapid. It's very fast, And also the rotation angle or the axis of rotation is also a little bit different. That is offset about 10 degrees. So there is some angular difference as well, the axis. If you take the core axis and the overall Earth's axis are about 10-degree difference, right? It's a 10-degree difference is there. So already the Earth's axis is 23.5 half 23.5 degree inclination is there. That is different thing. Okay, this 10 degrees the difference between the Earth's axis and the co-axis. Okay, that is how this magnetic field is generated. It's like a geodynamo, right? It's like a dynamo because of it is generated by the Earth. We call it geodynamo. So we call the convection as well there. Because of this rotation, the Earth's outer core behaves as a convective cell as well. Right? Do you remember the asthenosphere, the mantle, upper mantle, also has a convection cell. That convection cells cause convective forces for the plates to move. Right? Lithospheric plates are moved by these convective cells. So the similar thing is there in the Earth's interior as well, but of course the upper the regions of the mantle does not float on. I mean, they cannot move the mantle materials because mantle is not fragmented like the crust. If the mantle was also fragmented, then it could have moved, but it is not like there because of tremendous pressure. The mantle cannot be fragmented, so therefore it moves. I mean, the mantle does not move, but convection cells are there, convective forces are there, but which cannot move the mantle uh, relative to each other. I mean, the no fragmental uh, regions in the mantle, right? Because of high heavy pressure, it cannot fragment, unlike the crust. And one more important thing is this magnetic field reverse for some thousands of years timeline. So this has been observed by Earth's mid-ocean regions also. People have found in rock layers where the magnetic field has reversed. That means north-south has changed. Because once you have a north-south in a fixed direction, that polarity, we call it polarity, that polarity also adapts to the rock layers as well, because on the and that's why the bar magnet does not change its north south direction throughout the time, right? But after some hundreds of years later, if you hold your bar magnet, it might have rotated to the opposite direction. That means Earth magnetic field changes, right? Of course, it's not in a lifespan of a person, but it takes long time for that change, that magnetic reversal. We call it reversal of magnetic field anomalies, reversal of magnetic field anomalies, right? So these magnetic anomalies are also used to locate metal ore bodies as well, and also to find out deep uh, rock basins, because if the minerals are having different magnetic properties, we can detect that magnetic changes, right? Anomalies are detected because if something is deviating from the normal value, the average value, that is what you call the anomaly. It's like the gravity, right? If the magnetic property is also changing considerably, then you can think that that part is changing its magnetic property. So there should be something lying there. So then that region you can select and do the detailed investigation. So that's how the magnetic surveys are also useful for detecting mineral ore bodies, particularly because metals are sensitive for these magnetic properties, right? So geophysics, I think you also have a part of geophysics in your course with regard to some explorations as well. Uh, There you will learn about the details of these geophysical explorations of mineral deposits and even how can it be used for gem explorations to some extent as well. As I, although I said that normally these instruments are not used in geophysical, I mean, for gem discoveries, there are possibilities for finding gem deposits in very, very localized scale if you use them, but not in regional scale due to the limitations that I mentioned before. But actually, there are some other instruments now we call GPR, uh, global penetration radars. That is a radar equipment that can be used probably to locate some gem deposit. Actually, GPRs are used to detect metals inside. Right, metals means again mineral ore bodies, right? But sometimes that can be used to see some contrast in terms of mineralogy compared to the normal mineralogy in the earth's structure, where some concentrations of some particular elements can be detected, right? So in that case you can suspect, okay, there could be some gem deposits plus some implications from the geomorphology as well, right? Geomorphology means because you know normally to occur gem deposits there should be some basin, right? River basin, a paleo river basin exist. I mean previous river basin. That's why you have these rounded pebbles and all concentrated in a strata, that is a layer, that is what you call illama or anything, right? So there are such regions you can adopt this type of geophysical investigations and find out some changes to the normal situation. So then you can go for some extra explorations. uh, it's not impossible, right? It's possible. It's a matter of application anyway, right? But I don't see such applications worldwide yet due to such limitations that you have, because the cost, the expenses are too much to employ this to deploy this type of an instrument, right? So that is much cheaper than, I mean, the normal mining is much cheaper than employing this type of geophysical equipment, because they do not give you readily results for gemstones. But for ore minerals or mineral deposits, that's a very, very useful technique. In other words, we are detecting mineral deposits using these anomalies. Gravity or magnetic anomalies means we are trying to figure out the structure of the earth, right? So anomalies of the compositions of the crust, right? So that's why we were discussing this type of things as well under this lecture series. Okay, so so these anomalies are useful in understanding the earth's structure. So far we have discussed about the structure of the earth, and which is the composition can be different in terms of the materials. That's why we have this crust, mantle and core, right? That has happened at the very beginning of the earth. This segregation of materials depending on their densities and their chemistries has happened throughout the lifespan of the earth, even now being happening. Because magma generation means again some type of concentration of these materials into different rock types or layers, right? This is a continuous process. So these processes have now understood very well by different techniques, by geoscientists or geologists and physicists and chemists also. And collectively they have come up to a good shape in terms of the structure. In addition, we can just think of some special materials that might have in the earth, but at very local scale. Those are meteorites. So as you know, some places where meteorites are found, they indicate the very early earth signatures. Okay, meteorites may be representing the leftover debris during the Earth's formation. So in between Saturn and Jupiter and Mars, right? Between Jupiter and Mars, there is a belt of asteroids. The huge amount of asteroids are moving very rapidly. So some of those asteroids entered the Earth a few weeks ago. I think 1.5 months ago. Remember, in December, there were some meteorite showers, right? So these showers means part of the asteroid belt was very close to our Earth uh, while this rotation. So it happens once in some 200 or 300 years time, right? Because asteroid belt is always there, which is moving, and our Earth is also moving. Whenever we are getting closer to this asteroid belt, there are some opportunities for some of these asteroids to enter our Earth, right? That happened in December last time, after I think about 300 years later, right? So the next time, none of us will be alive to see that, right? So anyway, these asteroids are also found in some places in the Earth. Asteroids, once it comes to the Earth, it's burnt, right? Because of atmosphere. And a lot of the vibration and also the friction causes these materials to be burnt out before it reaches the Earth's surface, right? So that's why we see some sparking when it comes up as showers, as meteorite showers or whatever, right? So these asteroid, once it burnt, we call meteorite, and these meteorites fall onto the surface. In some places, people have collected them. They are very heavy. They are very heavy means they are undifferentiated, right? So not like the Earth. It's the material which was available at the time of Earth's formation. Once this material formed the Earth, the differentiation took place. Then only we had this crust and mantle or core or whatever. But these meteorites or asteroids, they composed the material of our ancestors, our ancestor planet, right? Proto-planet, the parental materials for the Earth form. So that means they are not fractionated. They are not changed into different layers, right? So these meteorites can be also found in some places where you can see some compositional differences in the crust, but at very localized scale. But although this localized scale, their effect is, they can be very large if the meteorite is very big, right? So Arizona crater, right? You just search in the Google about the Arizona crater in the United States. It's a huge crater formed as a result of a meteorite impact, right? In such zones, everything is changing, the composition changing, making a huge hole there, and even gravity anomalies, magnetic anomalies, everything will be there, right? So such local changes are also there, some thousands of kilometers, maybe some situations. So that's why in the Jurassic times, we lost everything, and the dinosaurs and all were died because of this type of meteorite impact, right? So although they are local scale, even some meteorites or asteroids are bigger than our Earth, the size. So they can even burn the entire planet, right? In that case, they are massive, right? So such compositions are also there anyway. To change the anomalies, the gravity or whatever, uh, the uh, the properties. So these are anyway the broken up planet or original material of the solar system, right? So these are the also a part of the Earth structure anyway. So that's why we take them also in here. So by this lecture series, what we understood was particularly about the Earth structure, right? Earth structure. So how this Earth structure is about, we talked much, and Earth's interior is probably uh, made up of many materials, right? Including meteorites, right? Meteorites are also there as part, right? That means undifferentiated materials plus differentiated materials. Differentiated materials means the parts of crust, that means rock types of crust or mantle. Uh, and the core, of course, does not have rocks. They are just metallic iron and nickel is there, right? So plus the meteorites are there as the composition of the earth. So most of these meteorites, as you can guess, they should have the age similar to the age of the Earth, 4.6, because that the meteorites which were formed which were available at that time are still there in the meteorite belt. So they should give basically an age similar to that time, right? Of course, there should be some older meteorites as well, because the age of the solar system is about 12 or 14 million years. So there should have been such meteorites as well, right? But the closest ones we have is the belt which we have in between the Jupiter and the Mars, which are mostly same as the age of the Earth. The Moon is also same as the age of the Earth, because the Moon is a part of the Earth which was separated at the very early times, at the time of Earth's formation, right? So the composition is mainly nickel and iron, the meteorite, because at the time of Earth's formation we had nickel and iron. That's why they sank into the middle part of the Earth. That means the deepest part of the Earth, as to form the core, right? Then stony. It can be stony, much like peridotite in composition. Peridotite means silicate, the mantle type of material, right? The mantle type of material. Uh, the crust is a product of mantle, right, for the Earth. So therefore, at the very beginning, we had only the core and the mantle, Earth. So meteorites are similar in composition then, into that original composition of the Earth. Crust came later. After melting of mantle, only crust formed, right? So that means it's a secondary type of product. Crust is a secondary product, not an original product. Original products are the core and mantle, right? So the meteorites are also same. Their composition mainly comes as nickel and iron, and also stony. Stony means rocks, but mostly like peridotite in composition. That means magnesium and iron rich. It's more or less the mantle composition, right? So once this is remelted, only this crust formed in our case. But the meteorites are not remelted yet. Therefore, they have this composition, right? Some meteorites are entirely nickel and iron. So these are called iron meteorites. And the other ones could be rocky type, that is stony type, mostly peridotite, olivine rich composition, right? Peridot, olivine rich composition. And some other varieties is also there. There is mixed type. So mixed type means both iron, nickel, and stony like. So it's more or less like our Earth's composition, this mixed type. So these are the varieties that you can find in meteorites. Even in some places in the Earth, on the surface, people find them very rarely, right? If in just for your general knowledge, if you happen to see any meteorite found, or if you collect any meteorite, if you found any meteorite accidentally, very heavy rock, because you are searching for gems, so you are usually looking for heavier materials, heavier stones, heavier minerals, right? So you might get sometimes a meteorite in a gem bed, right? Which was fallen some hundreds of years ago, hundreds of millions of years ago, right? Could be, right? Once if you get them, please make sure. It's very very precious, but I don't know how to value it. Maybe some valuation, but still, my concern is scientific concern. Actually, if you find a meteorite, you are bound to register it in the meteorite database. There is a global meteorite database. Actually, even though you find a meteorite, you can't claim that you are a owner of that, right? It's like actually gems. Like, even if you find a gem deposit in your doorstep, right, you cannot claim the ownership, right? You can exploit, you can get it, you can mine it, but once you get the license only, right? The Earth's resources are properties of the government, that is the legislation, right? So anyway, the meteorites also, there is, even a country cannot claim a meteorite unless it is registered, right? It has to be registered in a there's a global meteorite database. So you can put your name, part of your name, into the meteorite. It's possible, right? Because you are the founder, you are the one who found it, so you can put your name when you name this meteorite, right? There should be a specific name given to meteorite. Some standard is there. Part of that you can include your own name as well, right? But you have to register it, then you can have it, and you can keep it. But at least a part should be given to some designated places for analysis, right? For analysis, then only actually they register also, right? Before registering, you have to analyze it. You have to give a part to some standard laboratories are there. They will analyze it and confirm the composition, and then only you can register it, right? So you can have a part with you. It's not illegal to have a part, but you have to declare it. That's the thing. Okay, so this is about the Earth structure that we took some a few days of lectures, and we talked about basically the Earth's formation from a solar nebula, and then we talked about differentiation of the Earth, and then we talked about the processes that was taking place in the Earth's interior, including melting, the crust formation, and then about the plumes, how they hit the Earth's crust and fragment them and float them and move them, mantle convection and everything, the dynamics of the Earth, and how they change the configuration of the Earth, how the supercontinents are formed, how they are separated, dispersed, like that. And then we came to more details about the zones of tectonic regions, like subduction, collision, and hotspots and volcanism, mid-ocean regions, everything. We talked about their tectonic, or their how they are variable among themselves, rifting zones in the continents, and later on we talked about these puzzles, continental puzzles. That means plate tectonic theory. What else? Then we came how to understand the structure, the P and S waves, penetration of these P and S waves, and the anomalies of other properties like gravitation and magnetic properties and all, right? All these things we discussed, and finally we discussed about the meteorites as well, because that can also be considered as a part of the Earth. Okay, so is there any question regarding this content? I think this covers most of the part of my lectures. In case if I have something special or something else that should be taught to you, I will have a lecture later on. I'm not sure whether I'm taking a lecture next week, uh, but it all depends on the contents that we covered. And at the same meantime, you can ask me, or you can send me if you need some more clarifications on some regions. Then I can take some extra lectures as well to explain them or to elaborate them. But anyway, I will share with you the lecture notes from today onwards. I can send you, but I think you have to go through them again, right? Because you are not from the fields of earth science. I mean, everybody is not in the same background. Therefore, there may be differences in grabbing these stuff, and also keeping in mind also, because you are not like a full-time student, right? You are people who are working in the professional fields. So therefore, I suggest you that you go through these materials several more times, so that you can clearly understand. Because as a gemologist, as I mentioned before, uh, knowing these things is very important, because you have to be separated from normal gem trading community. I mean, you are along with them, but you have to step on one more step or level than them, because you are privileged to have a master's degree, right? It's not a normal degree, it's a master's degree you are going to have. So therefore, you should be able to show them that you have some extra knowledge regarding the formation of gems or their properties or whatever, not just the economical terms. Okay, so that is the importance of having this uh, type of lecture series. I mean the MSc series, but unfortunately, the current existing guidelines or the regulations does not allow us to recruit people who are not having a degree, a basic degree, to the master's courses, because the postgraduate institute of science, by its name implies it's postgraduate, so that means you must have a degree. It doesn't matter in which field you have a degree, but you must have a degree. So that's why we had limitations even in the past, but previously there was some provision for the people who were working in the field for 10 years or so, and also those who had some diplomas, IGA or whatever the types of diplomas related to the field, were allowed to be recruited for the master's course. But now, under the University Grant Commission provisions, we have no clear provision to directly recruit them. So therefore, now we are considering a path of for them as well, for such people who are working in the gem fields for many years, if they are interested in having a master's. So then we are trying to provide them a pathway also, some kind of alternative pathway, because there is no way for them to equalize a degree. That's the thing. Even a diploma, now everything is measured in terms of credit values, right? Number of learning hours, self-learning plus lectures, practicals, field work, everything. So that measurement cannot be taken for a person who don't have a degree. If anybody is having a degree, so everything is measured, it's possible, because it is done to a curriculum. So that's the thing. But once you don't have, I mean, a person who doesn't have a degree, then we have no way to measure his ability, I mean, the skills. His knowledge is there maybe in particular aspect, but it does not allow the guidelines does not allow us to recruit them. So anyway, we are trying to propose a pathway, alternative pathway for the future students. Anyway, that's out of the content of the lecture. But anyway, you can ask me if you have any questions. For time being, do you have any question? We have a few more minutes if I can spend if you have any questions. Otherwise, you can even send me an email or whatever the communication, doesn't matter. Once you read the materials again, you may have, I think, a lot of doubts you might have in the future. So anytime you can contact Dr. Dharmapriya or myself directly. It doesn't matter, right? I hope everybody has my contact details. You just drop me an email, then I can reply. Okay, if no questions, shall we stop then? So in case if I have extra lectures, I will be taking. Otherwise, for the time being, we will stop. And probably with another course module, we might meet in the future as well. Okay, so shall we stop then? Have a good day. everyone.
Yes, sir.
Thank you, sir.
Okay,
you,
you
sir.
are
Thank you very much, sir.
Thank you, sir.
Yes, sir.
you're welcome.